can move that if you want.
Oh, it's okay. All right. Welcome, everyone, to the College of Architecture and Design at Lawrence Technological University. And to those joining online through our YouTube channel, we appreciate you tuning in. Before I continue, please silence your phones. And just as a courtesy to the lecture also, I would also kind of refrain from working on your laptops as well, if possible. In an important announcement for freshmen who are here, this lecture is included in the newly launched University Experience and Engagement Passport program. So to get the digital stamp, you'll see the QR codes on the wall and on the table outside the door, and to fill in the form, okay? Welcome, everyone. My name is Li Su Huang. I'm an associate professor here at Lawrence Technological University, College of Architecture and Design. And I'm very pleased to introduce our speaker today. But at the college, we believe the future design is multidisciplinary, and we host a range of design degrees that include graphic design, industrial, transportation design, game design, interior, and architecture. We track design future trends, emerging technologies, and advancements in practice as a means of crafting education approaches in these areas. Our Design by Technology series allows us to engage in design discussions and offer broad perspectives on where we're headed. So just as a kind of PSA, register now for upcoming design and technology series events, both included in the Experience Passport program. Our next event is actually in 2 days, Thursday, September 25th at the Detroit Institute of Arts, where COAD will present Designing with Intelligence, an AI collection of speculative objects. This panel discussion will include experts who will debate how AI can be integrated into design practices, its impact on art and design, and how LTU is preparing the next generation of designers and architects to use these tools effectively. The second event is on Tuesday, October 7th, 12:30 p.m. Tasula Hajiani, Northrop Professor, Distinguished Global Professor of Interior Design at the University of Minnesota, will present a talk titled Design for Social Impact. So today, Mohamed Ismael is speaking about building for more with less, and at the end of the lecture, we'll have a little bit of time for a brief Q&A session. Mohamed Ismael is an assistant professor of architecture at the University of Virginia, where he directs the Open Structures Research Group. His work advances structural design and contextual fabrication methods to support sustainable development worldwide. Ismael earned his PhD and MS in building technology from MIT, where his dissertation, Reshaping Concrete, Empowering Development Through Low Carbon Structures, engaged nonprofit and industry partners to design affordable, low-carbon housing components for regions such as Kenya, India, and Mexico. He also holds a Master of Architecture from UVA and a BS in Civil Engineering from Duke University. His award-winning graduate thesis explored an urban vernacular building language for residential architecture in Khartoum, Sudan, utilizing form-finding optimization technologies while carefully integrating local resources, empowering local labor, and advancing local skill sets. His research has been published in leading journals and conferences, including Construction and Building Materials, Technology, Architecture, and Design, and the International Conference on Structures and Architecture. His teaching spans construction systems, structural design, parametric workflows at UVA, MIT, and Northeastern. Ismael's work has been recognized with numerous fellowships and awards, including the Paul and Daisy Soros Fellowship for New Americans, an MIT Presidential Fellowship, and the ACSC Diversity Achievement Award. Across his scholarship and leadership, he is committed to advancing justice, equity, and sustainability in the built environment. Please help me welcome Mohamed Ismael.
Thanks so much. All right, good afternoon. Thank you so much, Lisa, for the kind introduction, which I always struggle to sit through. So my name is Mohamed. I also go by Mo. I'm fairly informal. I know we have a Q&A at the very end, but if there are points of clarification or urgent things you need to ask me, feel free to interrupt me. Otherwise, I will proceed as a normal lecture would. So as was mentioned, I teach architecture and building science at the University of Virginia. And the title, I'll just say as a quick note, is not an accident. Originally, I used to call this lecture Building More with Less. And that was my engineering background kind of insisting that all I cared about was economy. When I was in India speaking with a really amazing engineer in South India about trying to find ways to engineer systems for housing, he jokingly said that my publication should be called Building for More with Less, centering the person. And to me, that's always been at the heart of the ethos of the Open Structures Research Group. We're a bunch of people, bunch of nerds in architecture, landscape architecture, engineering, with backgrounds in English, biotechnology, medicine, who are just interested in helping people with the technology that we have. And so ultimately, I like to say that we're trying to enable sustainable development through thoughtful structural design. We're seeing structures as just a tool. It's not the end-all be-all. When I was a student, I took this photo in Khartoum, Sudan, which, as Lisu mentioned, was where a lot of this research started. That's where my family's from. In the front, you'll see a clay pot called a zir. That is a public open source water source. So if you don't know, Sudan is northern Sudan is mostly in the desert. Water is a necessity to survive. And so it's not uncommon to see this really beautiful centuries-old technology of a zir, where it's basically a pot, clay pot, that allows for drip irrigation. You can basically put a little pinhole in the bottom, and it also happens to cool the water down really substantially. Anybody who's walking by can drink from it. Anybody who sees an empty zir can fill it. It is open to the community. And then in the background, you see another common site, unfinished concrete frame buildings. To me, it always felt a bit like a skeleton of an incomplete dream. These were homes that cost too much for people who were trying to invest in a future, but they couldn't afford it right away. And so they built what they could, and then they waited. And I hope you'll agree that that's, it's not a controversial thing to say that housing should be a human right. And so it always felt a little strange to me to see these unfinished houses just littered around. And this is not an uncommon sight throughout the global south. If any of you have traveled in Latin America, in South Asia, Southeast Asia, et cetera, you may have seen buildings that looked a lot like this. Most of what I'm going to be presenting today then is motivated by this question: how can we have dignified and accessible construction for the people that need it? How can we have an immediate and profound impact? I want to find ways to translate this rigorous design method that we're developing and we're working on to issues that affect 99% of the world's population. A lot of my work started by questioning architecture, and I'm going to use the capital A architecture for all of us and everyone outside of this, and our approach to sustainable development. There's often a really big disconnect between what designers in the global north, places like the United States or Europe, assume what designers need or construction needs in developing countries. We often romanticize indigenous materials, local practices, and we chastise the use of industrial materials like reinforced concrete and steel. But there is clearly a desire for structures that reflect people's desire for a dignified way of living, or something that signifies development, signifies achievement. And to me, that's a big part of why these investments were always made in empty concrete frames. So rather than imposing this romanticized idea of what low-carbon construction should be in the developing world, I wanted to explore an architecture of dignity that reflected their newer cultural values while still meeting realistic needs for construction. I'm not the only person to do this. There's some of my favorite designers from developing regions, like Anupama Kundu, Francis Carre, Miriam Kamara, have asked these exact same questions for decades. They've combined indigenous materials and practices with industrialized materials, and they've accomplished a whole lot more than we could have a century before. Nonetheless, these are often singular boutique designs. They're really beautiful little gems, architectural gems that you'll see scattered throughout the global south, but they're not necessarily scaling up. They give us a lot to learn from, though, and so I don't want to discount that. And so they're unable to meet the needs of so many people around the world, especially when we take in the challenge, the scale of the challenges for growing populations. This is a map of global urbanization over the next 80 years, and you'll see that the fastest growing cities are in the global south. The built area, you may have heard, is expected to double by 2060. You may have heard some of the statistics, like we're building a new Paris every week, a new Chicago every month. None of that's happening here. We don't see it, we don't feel it, but it's happening in places that show up on this map. And this is both an academic and personal interest of mine. I was born in California, but my family's from Sudan. I was raised in the Philippines. My parents now live in Kenya. All of these places show up on this map at one point or another. So it's not something we could ever really escape from. So, this is a house. My dad spent 16 years trying to build a house in Khartoum, Sudan. He's an expat. He has, I will say, above average resources for construction, and yet it still took him a decade and a half to build a house for his family that, if you don't know, Khartoum, Sudan is currently in the middle of a civil war and has been since the 2019 revolution, roughly. And so we're not even sure if this house is still standing, but it was a decade and a half of investment to try to build a home for his parents that no longer live. So it's a personal issue because they built a concrete frame building with engineers who didn't quite necessarily know how to work with this material. But he still saw it as a long-term investment that was more secure than the Sudanese dinar. So when I was a student, I started trying to figure out how my background in engineering and architecture could combine into some kind of interesting proposal where I could take the local material, not depend so much on imported materials like steel and some of the cementitious materials that were becoming more popular. And so I proposed this vaulted, dynamic system that responded to public and privacy gradients in housing in Sudan. But if I'm being honest, no one's going to want this. They want the concrete frame building. And so I was still working with this idea that I needed to reinvent the indigenous rather than respond to what was currently desired. This is another photo I took during my research. And what you might see is a family that has probably been allowed to squat in the property. And the reason for this is that they oftentimes were given permission to squat on an unfinished building with the understanding that they'll give their services to protect the building materials. And that, to me, highlights a really interesting issue, especially with our perception of construction practices. The economics of construction are very different in different regions. That should be obvious, but the point in case is that in a place like the United States, a more economically developed country, labor is the most expensive thing, and so we don't care about wasting material. We care about it from an environmental point of view, but economically we don't. So we will build modular, fast, prefab, wasting materials substantially. Whereas in a place like Sudan or other less economically developed countries, materials can be more than 80% of construction costs. And so it's incredibly important for them to protect those materials. They guard those for the decade plus that it takes to finish your house. And yet, a lot of the construction looks exactly the same as what we do here. Flat slabs, prismatic beams, regular column bays, and that's because a lot of the building codes, due to a very complicated history of colonization, post-colonization, building code adoption, building codes are not developed outside of a context. They are contextual. They depend on who decided to write them. And so they're often inheriting, like in Sudan, they inherited the British building code at that time. And so they were building with the same practices there, which assumed that you were building with Portland cement, which is a very specific type of cement based off of England, Portland limestone. So all of this to say, and I could go on and on, but I'm not going to today, because this is just a waste of time for now. It's basically to say all this is inherited practice. And so construction is beyond the means of many people, and to me it never really made a whole lot of sense. I'll also talk a little bit about embodied carbon. I just threw this in really quickly. Hopefully you all are familiar with the idea of embodied carbon, which is the carbon that's emitted for the materials and the construction, and sometimes the deconstruction, depending on the phases that you're considering in building construction. Right now, on average, 11% of global carbon emissions are just the materials and construction practice. And so it's not the biggest proportion of construction. But the reason it's so important is that it is the immediate emissions that we make. So we often talk about lifespan of a building, which might be 50, 60 years if we're lucky. And so we say operation, daylight, lighting, heating, cooling are technically most of our carbon emissions associated with the building. But in the first 5 years of a building going up, 50% of the emissions are most likely just going to be embodied. And so if we're already suffering from a climate crisis, it makes sense for us to focus on the immediate carbon emissions. And so that's where it becomes a big focus. Now, I also work a lot in concrete. Concrete has become completely fairly so a villain in a lot of ways, and I think it's actually more a victim of its own success. Today, if you don't know, 2 times as much concrete is produced as all other industrial construction materials combined. It is far outpaced any other material in the world, and there's a lot of reasons for this. Some of them I highlight here. It's affordable, it's available, it's fire resistant, it's durable, but I think most importantly, it's trusted. For about 100 years, we have not really changed reinforced concrete construction. It's stayed about the same. If I look at Francois Hennebique's systems from when he first started patenting regular concrete frame buildings, they don't look very different from what we're doing today. And so that might be worth questioning. Also, this is a projection that by 2050, most of the concrete cement production will outpace that of China. Right now, China is the largest producer and consumer, but places like India, Africa, South America are quickly outpacing China. And so it's expected that the developing world, just in general, will explode due to this urbanization that I talked about earlier on in their use and production of concrete. So I said 11% of global CO2 emissions are related to building construction and our materials. In less economically developed countries, it's 2 to 3 times that. And so their carbon emissions are much more heavily proportioned towards construction because they're building at a faster rate than us. So it's really important for us to, again, contextualize the numbers and not just say the global average is the global average for everybody. Making sense so far? I'm throwing a lot of numbers, so hopefully I'll bring some photos and images later, but I just want to set the case. There's also this really interesting misconception that concrete doesn't belong in these regions. These are just a few of my favorite concrete structures in the world. Concrete's played a key role in pre- and post-colonial, less economically developed countries for decades. I think some of the most heroic, creative uses of structural concrete in the world happened outside of the global north or the west. This is a concrete reinforced port-in-place space frame structure that was built in New Delhi, the very first one, the Hall of Nations, by a brilliant engineer, Mohamed, and it's the only one that's ever been done in the world. And the only reason it happened was that labor was so cheap and materials were so expensive that they had to come up with a more creative solution. Buckminster Fuller visited this project, said that they didn't know what they were doing with the material, and Mohamed laughed at him and said, "We know, you just don't understand our context." He didn't understand that they were carrying buckets of concrete on their head rather than having trucks bring it in. They didn't have factories for steel production. It cost 30% more to import the steel necessary to build a space frame out of steel like Buckminster Fuller would have suggested. So context is everything. And I think there's a lot more to draw from there, but I will move on. Today's construction challenges in my mind lie a lot in what can be done for housing. Residential construction uses about 40% of global concrete production in the world, and it's actually more in LEDCs. It's usually 65 plus. And then when we look specifically at the building system, when we talk about concrete buildings, multi-story concrete frame structures for housing, horizontal spanning systems, which is a fancy phrase for floors and roofs, constitute 50 to 80% of structures, carbon, and mass. Okay, so that was a very long-winded way to explain why I work on concrete floors. I've spent the last 10 years just designing concrete floors, essentially, if you want to whittle it down. But hopefully it makes sense why. Have all of you taken structures at one point or another, or about to, or going to? For those of you that have, I'm really sorry for this slide. This is a beam shear and moment diagram. I teach structures, so I have to teach this every year, and it's the bane of many students' existences in architecture school. But it's important. Galileo discovered beam theory in like the 1630s. He also wrote about elastic theory. A lot of our structural principles came from some of the earlier Galileo experiments. And he realized 400 years ago that the stress or the amount of force that every part of a beam is taking is not the same. Yet we design them for the maximum. We always take that maximum moment or that maximum shear, and then we size our structures accordingly. And so if you do this in structures, you'll do the shear and moment diagram for all of your boundary conditions, and then you'll pick that maximum and you'll choose your cross-section size, and you'll say, that's the size I need. But the reality is most of the structure is under-stressed. And so if we take Galileo's principles and adapt them, we find that we can save some material. We can cut some things off and still be safe and still be within the parameters required for building codes and all of the things that are necessary. We already do this in principle in practice, where we go from flat slabs to CT slabs to waffle slabs like you have in your student center. Those are all variations, but they're still prismatic. They still have the same cross-section all the way across, but they are kind of building off of this idea that the entire structure is not always stressed exactly the same. And so if we can take that principle a little further, we have this hypothesis. Through geometric complexity, we have more opportunities for material efficiency. And it doesn't necessarily mean I have to go for the most complicated, most efficient structure all the time. This is a really early study we had done where we basically proved there's a gradient of solutions. If I change how complex my structure can get, I can save a little bit more each step. And so if I go from a flat slab to a ribbed slab, there's about a 40% drop off in the mass and embodied energy. And then if I keep going further, I can save up to 70% at some point of just the material consumption of a slab, but it does not have to be the most complicated solution. And so that turned into this really complicated method of structural optimization where we can take numerical optimization, which is basically you bring in things from computer science where you iteratively improve your solution, you check that solution, and then you keep adjusting until you end up with something that is both safe and efficient. But we don't have tools for all of this. Most architects don't know how to design concrete structures because it's complicated. Even a lot of engineers don't know how to do it. It's a very specialized set. And so a lot of my earlier work, especially my doctoral work, was developing tools and methods that most people can hopefully access using just basic mechanics and analysis that a lot of architecture and engineering students would have learned, but may not actually practice in practice. So I just show these formulas to show that I know what I'm talking about. I'm not going to talk about them really. But we determine how much shear, how much bending there is, how much stress there is in each section. We needed to come up with a method where if I just gave you an arbitrary cross-section, could I figure out how much steel there is, where that steel is supposed to be, how much concrete's in compression, and how strong is that entire section? And we need to do that quickly and automatically. And so we brought that in. Ductility, things like how much steel there is to make sure that the beam doesn't crush before failing, that it has a safe failure. We call it under-reinforced so that the steel is engaged. There's all these principles that are embedded in the sort of philosophy of our building codes, but they don't require us to build an exact rectangular beam all the time. We can accomplish this in any geometry. Deflection. A lot of times people don't realize that engineering is not just designing for structural safety. We also want to make sure that our floors don't bounce so much, or that our wall finishes don't crack, our paint doesn't crack, our paintings don't fall off the wall. And so all of these principles can be embedded in this design method. And so this turns into a constrained optimization problem. I want to optimize some kind of cost, and that cost could be the cost of materials. It could be the cost of fabrication if we're able to quantify it, the embodied carbon. I have some kind of geometric variable set that controls the shape of an arbitrary geometry, and it's subject to all of the structural and non-structural constraints that I mentioned. And it ends up looking like this. This is a shape slab optimization. It's sped up a little bit, but basically this is what you would see if you were using the tools we developed. We have publications about it. I'm happy to share. The tool is technically open source, but it's very much in beta. And so we're still trying to figure out how to get it in the hands of people, which I'll talk about in a second. But this is the shape optimization for a 6-meter beam. You set up your spans, you set up your variables, and then you let it optimize. And every time a cross-section turns red, that means it's not meeting one of the requirements, at least one of the requirements. And until they all turn blue, it's not satisfied. So that's the whole point of constrained optimization. And we can do this for single beams, we can do this for entire structures. This is the tool Radical, which is another plugin that was developed by our research group at the time for constrained optimization in Grasshopper and Rhino. So we wanted to make these tools available to designers who might use CAD and put them in their hands much faster than if you had to require an engineer to be involved. This is great. It's strong. It works really well. It gives you solutions that would be really hard. It's basically doing calculations that would take about 10 minutes by hand. You're doing 400 of those every second or every iteration, and then you're doing it 500 times in a row until you end up with the right solution. That's next to impossible for an engineer to do by themselves. And so an engineer could do this. It would take months to end up with a design that takes us about 40 minutes. So it's great. It gets us somewhere. And so the hard part is obviously making this available to people. So one of the first things we did is developed a open source tool called Beam Shape Explorer, which essentially captures that complicated part that was missing from that big workflow. And we made some plugins where you can put in the building code that you're working with, the material properties, how strong is your concrete, how strong is your steel, how much does it cost? It does all of the geometric principles, the structural analysis, it puts it all together, and it just kind of fits into tools that already exist for optimization and for structural analysis. So if you've heard of like Galapagos, which is a really popular one, or GOAT, or these tools already exist. Design Space Exploration is another one that also exists. We're just kind of filling in the hole to get this workflow out there. And we know that this works because we've had colleagues who've used this in their research already. This is some work that was done on robotic 3D printing of self-supporting vault geometries as a formwork for a concrete two-way slab. And so when you think about it, robotic fabrication kind of frees you up. You can have every single pot of a waffle slab look exactly the same, or you can have every single one of them different. And because of how digital fabrication works, the cost is about the same. And so that frees us up to do some optimization. We can save some material. We can also start to bring in other principles. I can talk to someone who's an acoustics specialist at Penn State, and he can combine his acoustics with the structural design method. And we've simplified the structure part, so then you can start to bring in other performance metrics that matter. And so this is Jonathan Broyles, who did his PhD on structural acoustic optimization of concrete structures. Edu Gascon at MIT did his PhD on thermal massing. As you probably know, thermal massing is essentially the storage of energy or heat energy inside of a structure. It can be a really powerful tool for heating and cooling spaces all around the world, therefore reducing our reliance on energy or active systems. The problem is most of us don't understand how thermal mass works. It's a complicated system. And so Edu has spent his entire PhD trying to figure out how to quantify it and how to actually look at these floor systems as radiators or ways that you can store and heat buildings at different places. And so this is looking at how my initial savings of embodied energy at the very start, or embodied carbon, is that kind of first drop. But if you were able to quantify this over the 60-year lifespan of a building in Cairo, you could save over 60% of its entire lifespan of carbon emissions. And so that's heating, cooling, and structural. So a lot of different things going on, which is cool because it opens up to a possibility where we're not just designing one structure for every part of a building. We can design it for different programs. We can have more specialized systems if we're kind of projecting this way in the future. Now, I did mention all of this takes 30, 40 minutes, depending on how complicated your problem is. Sometimes it's 5 minutes. That's not realistic if we're trying to design a structure in real time. Most of us are not thinking about our beam designs when we're at the massing scale. But a lot of research has shown that the earlier we think of these solutions, the more potential there is to save carbon later on in the project. And so how do we bring this to the early design stages where I'm still just sketching and trying to figure out where my program goes and where my columns go? And thankfully, we can borrow a little bit from machine learning and AI. We can use early stage design surrogate modeling, where we just kind of build a set of samples which are based off of general problems. So I could say, I don't necessarily know how much load I have. Load will depend on whether or not this is an office or a library building. And so I can put all that in, feed it into the optimization, generate sample upon sample, map it out, and I get this weird mess of a plot where I don't actually know which solution is best. This is 2,500 different samples of optimized structures for different live loads, different spans, different depths, different strengths of concrete and steel, all of the variables that I might play with early on. I can't really read this plot. I don't know if you can. I can start to pick out some things, say like the lowest 25% kind of seem to have these characteristics in principle, or the highest 25% does this, but it's still not totally legible. And I can plot out some of those variables and see that generally speaking, the orange dots are the optimized structures, the black dots are the regular structures. Generally, orange seems to do better, but there's no logic to this. It's kind of chaotic. And that's because the mapping of this design space, is what we tend to call it, is really complicated. This is like a 10-dimensional space that I can't actually visualize on paper. But I can still use that data to build a predictive model, because mathematically there can be some approximations. And so this is the architecture of a neural network, very basic neural network that allows me to put in some of those design inputs and optimize or predict what the optimized result would look like. So that was a lot of mumbo jumbo about how these numbers kind of come together. Essentially what I'm saying is that in real time, I can play around with some of those number sliders, and I can say, what if this were a house, or what if this were a library? And in real time, it'll tell me how much concrete I'm going to use, how much steel I'm going to use, how much carbon I'm going to be using, what the cost of my materials might be. And I can compare different models. I can do a flat slab versus a shaped slab, and I can show people, as we're just kind of iterating through these designs, how much they might save if they took on this more complicated structural design solution. And I said real time, so it's worth showing a video of me actually doing this on my little laptop, of using this predictive model. And so this is not running an optimization, it's predicting based off of optimizations. And so I can, with a very generic floor plan, start to figure out how big are my columns going to have to be, or how big are my beams going to be, way earlier than you normally would in the design stages, where you might bring an engineer as a consultant in. And To me, what was cool about this is we could start to bring this in with non-experts. So we ran a user study last year with some students using a MetaQuest 3 headset, and they're working with that generic model in a Grasshopper environment using Follogram so that it was projected inside of a part of our building. And so they're seeing the impact of their design choices. They're seeing these shaped structures, and then on that little board, it's telling you how much steel or concrete you might be saving in comparison to the original design. And they get to decide, do I care about embodied carbon? Do I care about mass or concrete? Or do I just want to make the coolest, weirdest thing I can? All of that is up to them. Okay, none of this matters if we can't build this. And so a lot of what I'll talk about now is just experiments we've done over a few years to prove that these systems are doable. And we've done this at both small and full-scale prototypes. And a lot of this is informed by existing practices. So I've already mentioned that we have industrial systems that exist. We have waffle slabs like you have on this campus. We have hollow core slabs. Bubble deck is a newer system. All of these have potential reductions in embodied carbon. The reason these haven't been adopted at the scale that we would want to see for these solutions is that they often require a huge amount of capital investment. You have to build factories. You have to build the facilities. You need the infrastructure for it. And so a lot of developing countries don't have that already in place. There's investment opportunities and people trying to make this happen, but they haven't quite scaled up the same way. Precast concrete in the United States has existed for decades, but it's still not a majority of our concrete construction. It's only about 15% of concrete construction is precast. And so we're under an illusion if we say these are the immediate solutions. In academic research, there's been a lot of really exciting work done by colleagues where they've found ways to use digital fabrication, ultra-high performance concrete, robotic fabrication, to build really creative and inspiring solutions, but they often are requiring fabrication methods and materials that are either not available or not in code or too expensive. Ultra-high performance concrete is about 300 times the cost of regular concrete. And so it is an amazing material, and you could potentially save a lot of material. Also, 300 times might be wrong. I think that's an outdated number, so don't quote me on that. But it is more expensive than standard concrete. It's becoming more accessible, but it's still not quite there. And so what we've been really interested in are accessible ways of designing and fabricating these things. Really simple study that we did at UVA last year was trying to just look at the materials that we use in our studios. A lot of students have been advocating for the removal of XPS, extruded polystyrene foam, because it can off-gas carcinogens when you're cutting it on a wire cutter. Certain students have been worried about the material just being in their studios in general. And one of the issues that frequently comes up is that we don't really have a great alternative for casting. We don't have a great material that we can cut, that's cheap, that's accessible, that we can cast whatever we want, our mastering model, our final model, whatever, out of it. And so this was a great chance to bring in some of the research we had already been doing and just say, okay, what are some of the materials that are available or materials that we're interested in? What are things that we assume are going to be low cost, low carbon in comparison to XPS, and let's actually test them and quantify some of these assumptions. And so we started this by just mapping out where our materials came from. Turns out our extruded polystyrene, a lot of it's actually coming from inside the United States. Almost every other material we're considering comes from around the world. And so they might be low carbon from a material sense, but their transportation is actually a huge issue. Doesn't mean that they're not equal, because it's just worth considering where they come from and being honest about that reality. And so we looked at materials like cardboard, cork, reeds, which often are imported from places like Indonesia, bamboo, which we actually found in Charlottesville at a local Japanese garden. Landscaping fabric is another way that you can build complicated forms, and we started to actually quantify what is our embodied carbon. So you'll see that certain low density, it's really small, I apologize, cork, technically, you can argue that it's a negative embodied carbon material because it's a natural material that draws carbon from the environment. But because most of the cork is produced in Portugal and then processed in either China or Canada and then brought to us, there's a huge carbon footprint that comes with it. This small bar at the bottom is XPS. That's the original polystyrene foam, or XPF, sorry, polystyrene foam that we're dealing with. Then we look at the cost of the material. How much does it actually cost to use it? Cork, which was the one that my students were most excited to experiment with, was the most expensive one. It's a beautiful material. It actually gave us a great finish. Things like cardboard, landscape fabric, which were super cheap, low carbon, tended to be really hard to work with. So it took, this is labor in hours, just how much time our students were working with these materials. And so the whole point of this, the conclusion of it basically was that there is never a clear argument between which material you should choose for whatever. It's the same thing between mass timber and concrete. If you don't have the supplies of mass timber, then concrete makes sense, and vice versa. And so it's important for us to be honest about these reflections. And so we presented this work at the school to just kind of showcase what can be done with what is readily available here, things that you might order from Amazon or Walmart or get down the street at the local art store. And we tried to just give an honest reflection of what's done. We also documented and published some findings on this over the summer on the finishes that you might end up with and what tools you might use. Are you using a CNC router or using a laser cutter? All of that factored into how accessible these were. Then that on top of the sort of smaller scale, lab scale work we've been doing, we've been lucky to work with a lot of really great partners around the world for full scale fabrication. So this was a 5-meter prototype, so about 15 feet prototype that we did in New Delhi in India a couple years back. And we designed a system that met India's code and used 50% less material, but ultimately it was built using all the exact same concrete and steel that is available to builders there. And this was a great sort of humbling moment where I was asked to challenge my assumptions. I thought that I could get foam for an initial prototype at the scale that we wanted. Due to land pollution issues in New Delhi, we could not find foam. Nobody can sell foam at the scale that we needed. And so that meant that we couldn't use a CNC router to route this complicated 3-dimensional structure with 2-way curvature. That would be really hard to build by hand. So our local partners offered to do it out of 3-inch steel blocks and basically mill the steel blocks until we got the shape we wanted, which is insane if you think about it. I mean, it was great because they wanted to make our dreams come true, but that was not the right way to do it. And so we just had a conversation with them and we found out that they had 20 years of experience working with plate steel. Plate steel for formwork is a really common material for especially affordable construction because you can use it up to 200 times plus if you oil it and take good care of it. And so it's an expensive initial thing, but if you have the skill and labor for it, they can build a formwork like this. It was a formwork that kind of came apart in 4 pieces. We did not tell them how to design the formwork, they did it themselves. And I forgot to mention that the partners we were working with was a local nonprofit that specifically works on affordable housing in rural areas of India. And so they had a lot of practice working with what they called small and medium scale enterprises. Unlike in the US where we might have big precast companies that can transport things 100 miles, in India you're usually working with a family that's in a close neighborhood and they sell the block product to people in that area. So anytime someone wants to build a house or an extension or another room, they're buying it from their neighbor and building. And so they had skill and knowledge at working at that scale. And they believed that this was the right way to do it. We also got to test it at the National Cement Lab in New Delhi, or Faridabad, right outside of New Delhi, and proved to the engineers who were very skeptical when they saw the structure that it met the code requirements. It wasn't too flexible, and it was strong enough to meet all the requirements for residential loading. So the white line is the predicted load that we had done on our computer through analysis, and then the orange is their actual behavior. And so we often end up doing structural testing because until you actually test this in front of people, people are not totally convinced that it works. This turned into another collaboration with some amazing professors and students at the University of Arkansas. We built another prototype in Arkansas. One of the things we found in India was that even though you can design and build the coolest 3-dimensional form, the actual translation to fabrication is always the issue. There's a sort of misconception that digital fabrication is a high-tech thing that's inaccessible to most of the people in the world. The fact of the matter is if I look hard enough in New Delhi, I will find somebody with a 3D printer. I will find somebody with a robot arm or a plasma cutter. But we still have to figure out how to translate the design from 3D to 2D pieces. And so this was a really great excuse to work with some partners of mine. Edmund Harris and Emily Baker at Arkansas. One was a math professor and was an architecture professor, and they had already been developing something they called ZipForm, which is a way to mathematically translate 3-dimensional curved surfaces into 2-dimensional flat objects. This was a specialty of Edmund, and Emily does a lot of fabrication. And what was cool about this was that it just required a very simple jig that Emily had constructed with students who had never worked with metal before. Whoops. Let's see if this works. Yeah, okay. So the jig is basically pressing these 2 flat pieces of steel together, and then you're just spot welding as you go. So it's a really fast fabrication method. And what's cool about it is that it removes all the guesswork. So if we could bring the design method of zip form and put it into our constrained optimization method that I talked about earlier on, you basically end up with formwork that can just fit together like a bunch of puzzle pieces. And so it was relatively easy to assemble the whole thing. And so we ended up with a formwork that was more reliable, and we got to test it once again in Arkansas's new civil engineering lab, where we had some PhD and master's students actually documenting, as you can see down there, the cracks that are occurring, basically proving that we end up with what we call a ductile failure, which is a safe failure mode, where if your beam is under load or in an earthquake, you don't want it to collapse suddenly. That's a brittle failure. Ductile failure is basically small cracks that are slowly creeping their way up, and that way we have time to assess the damage, we have time to evacuate, repair, whatever. And so we proved that we could end up with that ductile failure, which is basically a little plateau that comes off at the end instead of the load just dropping off. Does that make sense? All right, cool. Just checking that you're all awake still. Okay. Okay, this is one of my favorite prototypes in Mexico City in 2022. We got to build an actual almost room scale example of a shape optimized structure, again, saving 50% of the mass. And this was cool because it started as a conversation during the pandemic with these affordable housing builders in Mexico City who were using something called incremental housing, which is a long-standing policy. It's basically the cheapest way to give housing to as many people as possible, where you build just the core unit, which is usually kitchen, bathroom, 1 bedroom, and then you provide it to the family, and you kind of guide their construction in the future if they're able to afford it. And so we took the most expensive part, which, as I mentioned before, was the floor system. So if you had a 3-floor building, that might be the most expensive portion, and we showed that you could optimize this system. And this was a good example of what I was talking about. We originally didn't plan on 3D printing clay for this, but we happened to find a great collaborator who had already opened a 3D printing studio in Mexico City and wanted to try this out. And so what that meant was that original argument that the more complexity we have access to, the more we can save. We were able to prove that if you had a 3D printing arm, you could shape every single block completely differently for the same cost as designing all of them exactly the same. And so we ended up with this sort of tapering solution, but the widths of the beam stay the same. And I forgot to mention, block and beam is a long-standing system that's been used since about the 80s in Mexico. It exists in other countries. And the reason it's really popular is it's a great way to build larger structures with very small pieces. And so you have these prefab segmented little beams that you can buy at a local shop, and then you have the blocks that span between them. The blocks are just there to hold the weight of the concrete while it's curing, and then once the concrete cures, those blocks are essentially lost formwork. So they aren't necessary for anything after they're done. But it's a long-standing tradition, so people are very familiar with how block and beam systems look. And so we got to build a prototype in the middle of Alameda Central. HLA was our local contractors who had a lot of experience building this. And we didn't actually get to structurally load test this the way we wanted to, but a couple thousand people visited it. This young lady did some lateral testing for us. It did technically survive 2 earthquakes, but the epicenter was far away enough that I don't brag about that. But they were like magnitude 5 and 6 earthquakes. And so it was cool to be able to brag that our structure, which was not actually finished, we didn't glue anything down, there was no foundation, but we did design it so that there was no overturning moment. There was all these things that we put in place that I'm really grateful that we did, because it could have fallen during that week that it was up. And it garnered interest from people who saw the system as something that resembled their housing. It was just a slightly different version. It didn't look too alien. So we had post-tension walls and calculated the overturning moment. So what you see inside there is a little little exhibition piece where people could come and put little postcards for their dreams of the future of housing in Mexico City, or the future of Mexico City. And so it was part of a larger collaborative effort, but it was great to see it in person. Now we're working on a similar prototype in Nairobi, Kenya. Nairobi is one of the fastest growing cities in the world. It's growing at a rate of about 22 people per hour, which is a little hard to think about. Nonetheless, it's facing a housing deficit of over 2 million units. Over 70% of their population live in informal settlements, in massive informal settlements like this. It doesn't mean that they don't have housing, it just means that they don't own their land, they don't have the infrastructure, so they often are self-organizing. Kenya is also one of the more aggressive countries in terms of climate policy. I hope you'll agree when I say that Kenya is not responsible for most of the climate change, but they're already suffering a 3 to 5% loss in their annual GDP just due to droughts, due to flooding, climate migration. They're having a huge amount of issues, so they're being more aggressive about this. They're being more forward-thinking than certain countries like ours. And so just like a lot of the other countries I've worked in, materials make up about 70% of construction costs. And so developers have actually reached out to us and asked how we could use some of our research to work there. So we're hoping soon to build a prototype yoga pavilion with this locally owned family business that actually does regular yoga classes in the middle of this beautiful forest in Nairobi. And we want to use it as a way to show that one system, namely the zip form system, can be used to design formwork for many different types of beams. And so it'll be a simply supported beam, a cantilever beam, a double cantilever, just showing that different boundary conditions can be built using the same formwork system. And we're doing this with a local steel fabricator named Framework, who already have a lot of experience working on modular construction and modular formwork. This was a video they sent me about 2 weeks ago of their first prototype of a beam that I just sent them a Rhino file, and they were able to make the zip form themselves pretty much without instruction, which was great to see. And so hopefully in the future we'll build this. We've also been in discussion with precast concrete construction companies in the US to work through the obstacles to adoption. As I already mentioned, the economics are different for construction. And so a lot of times people see these systems in the US and they say, that's great, but we don't have time or capacity to do anything that would slow down production on precast, which already has incredibly slim margins and is already struggling to keep business the way it is. And so we recently published a very small paper just kind of questioning the costs of precast construction. And the question, or the answer, is that it's really complicated. It's labor, it's materials, but almost more than anything else, it's logistics. If timing, if your concrete takes a little too long to cure or cures too quickly, that throws off the mechanics of everything else. And so we're working on actually documenting through lit reviews of structural design, detailing, fabrication, transportation, material sourcing, and much more. And we're seeing what kind of shape optimization research has already answered and what are the gaps that are missing. So we're not really saying that we have all the answers, but everything, and this is just a really boring table, but basically the things in purple basically mean that there's a gap. There's something that we need to question further. And then we have spoken with people in the industry and asked, like, what manuals do you have, what resources do you have, and how do they overlap with academic research? So we're really hoping this just kind of opens the doors to a larger conversation where we can take this optimization method and these tool sets that we've developed and actually put cost into it, a realistic cost metric, because until we do that, nobody really cares. I'm going to end on this last thing, which is that outside of academia, I'm really lucky to be working with colleagues who are either at MIT or just left MIT to take what we've learned and make innovations accessible to people at a global scale. So we launched a company named Forma about a year ago, and we've been building and testing our ideas at full scale together for about 5 years, but now we're actually trying to bring this to practice. So our team consists of these three brilliant recent PhD graduates, and then I'm one of the scientific advisors along with Caitlin Mueller and Les Norford at MIT. And we're developing pilot projects with local manufacturing companies in New England area to validate what we think is possible in terms of cost savings. So this is the first time where after 8-9 years of trying to get companies to actually help us figure out the market, that we just decided to do it ourselves. And so we're doing the market research, we're investing the time and energy to figure out, okay, how much does it cost for a small plant to try a different design? How much does it cost for them to actually change one of their beds in a precast plant and save some material, even if it changes some of the complexity down the line? So some of what we've managed to accomplish is that Mexico project I talked about actually turned into our first customer, where La Trilera is a company that produces affordable housing block and beam systems in northern Mexico, and we've been working with them since 2024. We've also recently won the MIT Climate and Energy Prize and the Massachusetts Clean Energy Center's Innovate Mass grant. So these are all recent developments, but it's to me a signal that the industry is interested and that they're actually trying to invest in this. And so hopefully we'll be a part of changing this. One of the first things that we're working on, and this is just a sort of draft video and development of a tool that takes all of the concerns that a precast company might have and puts them into a tool that uses that predictive modeling I talked about earlier on to show you that if you were to change this dimension, or give yourself a little bit more complexity in this regard, how much you might be able to save, and can you justify that? And we're trying to make this as simple as possible. We're removing the CAD environment. We're making this a web tool that people can just iterate with. And this is early stage design, where a company that might be building a parking garage might find that they can save 30–40% of their concrete if they just modify like one dimension a little bit. And we're starting to gain some traction there. As I mentioned, this was our very first work, which was working with this company, and this is Edu Gascon, who was interviewed for local news talking about this design that we had done, which was basically just a 16% saving. So it's not a huge number, but it doubled their profit margin because their profit margin was already slim. And so they saw this as an obvious yes. They've already started producing this. Hopefully we'll start selling it very soon. And what's cool is that these companies don't work in isolation. When one company kind of builds up a system and proves that it can be competitive and meets all the local codes and is more affordable, other companies start to take a hint. And so we're excited to see where this goes. And I will stop talking there. Thank you all so much.
Grab the
Sure.
roving microphone. And can I see if there are any questions from the audience right away? No? Maybe while the audience stews on things, I think this is a kind of very interesting take on, like traditionally, let's say we would have kind of thought about design, computation, digital fabrication as something that's used for, high-end Apple, right, Google, right, these sort of like headquarters things. I think it's really interesting to see it being applied in these sorts of contexts. I think maybe just to kind of start a question about what kind of, and there are some examples in here. I'm very curious about, you're mentioning that you can actually find both like the kind of idea of both like local craft expertise and then sometimes even some of these advanced tools in India and contexts like that versus the US, right, or Europe, right, where we're kind of like heavily industrialized. But the sort of like both like the labor costs and the sort of machinery costs are maybe barriers to entry even for advanced countries like the US. And what kind of barriers are you finding? What kind of opportunities are you finding in these sort of two opposite contexts?
Yeah, that's a great question. I'll start with, I guess they can kind of be simplified or combined. I was thinking about like developing versus develop. The main point that we in our research want to break down is that there's, in my mind, no such thing as a low-tech and high-tech context. Really, everybody with the right information and resources should have access to a lot of the different technologies, as long as someone considers it worth investing. And so I can find a plasma cutter in New Delhi, and I can find pretty much every precaster I talk to has a CNC router or some kind of laser cutter, and they just use it to build the same thing over and over again. And so I think what's actually interesting, just like how the robotic arm became sort of this beautiful tool in architectural robotics, but started as a repeatable tool for the automotive industry. And we just found ways to make it a little bit more creative. I think it's the same thing with just going back to basics with laser cutters and plasma cutters, where if we can develop, and I think it's really just about what's that missing, the slicer technology that was so revolutionary for 3D printing, where it takes a 3D volume and turns it into layers for a 3D printer. We don't really have that for most fabrication, digital fabrication techniques. And so a lot of people have started working on this for path planning for robotics, but we haven't really gone back to basics with just like, how do I translate a complicated form like this into sheets of steel or sheets of plastic? And I think that's where we can get really creative with computational fabrication. And I don't think it matters what the context is. Everybody can benefit from this. Yeah.
Great.
Oh, Ralph, I'll just shout out. Awesome presentation.
Thank you.
Amazing work.
Thanks.
So, and you may have an idea about an answer to this question. But could you tell the reasons why you even pursued fabric forward?
Oh, yeah, that's a great question. So just to reiterate for people on YouTube, you were asking why not using fabric formwork, which Mark West was obviously like a huge push for in Canada at the University of Manitoba. If you don't know, I did mention very briefly that we tried some fabric formwork, and I've tried fabric formwork multiple times in my career, especially at the very beginning.
I came in a little late too.
No,
actually,
totally
sorry.
fine. Because I avoid talking about it specifically because it is an amazing technique. If you don't know, it's a way of using fabric to form complicated shape geometries, and you end up with really beautiful sculptural forms. It is one of the hardest crafts to in my opinion, to actually get a handle on. It requires a really innate understanding of fabric and its mechanics, one that's not taught easily and not translatable. But if you have the skill and background, so I had a student, that study I talked about where we tried different formwork materials, I had several students and each of them chose a material to work on. The student that chose to work on fabric formwork was about a month later than everybody else in building his form. It ended up being one of the best ones, but it took him so much more time, iteration, and practice to figure out, because in my opinion, it's an amazing craft, but it's still a craft that isn't as widely scalable. So I think what's really cool about a lot of the advocacy for fabric formwork is a bigger argument that maybe construction should be going more back to crafts. And I completely agree with that on many fronts. But if I'm trying to be realistic about ways that we can accomplish the scalability of housing people as quickly as possible while reducing our climate impacts, I have to be honest about my skepticism about whether or not a craft is able to accomplish that right now. But I don't think it means that we shouldn't be doing fabric formwork. I think I would love to see more of it. The only building I've seen with fabric formwork, and maybe you know better than me, was a school built in Cambodia.
So they've been doing, the group doing a lot of work over there.
It was amazing. They still ended up building regular rectangular forms. It was just with fabric form because the rebar bending was so hard and complicated to do. So even the engineers admit that there's a limit. And then really amazing research by John Orr in Cambridge. When I started my research in India, he spent quite a bit of time talking to fabricators in India to try to get fabric formwork to work there, and it never picked up. And so I'm not an expert on this. I just know that there's been a series of attempts by people who know way better than I do. And so I took that as a hint that maybe I should try other things, but
well,
not
part of my
against.
curiosity
Please.
too is I just love the idea of concrete as it goes from a liquid to a solid.
Yeah.
And if the formwork could preserve the liquid qualities, I think that's really awesome.
That's a really
That's just
interesting
magic.
idea. I love that. Yeah, no, that's a really great idea. Thank you.
Any other?
Yeah, thank you for take a breath, because that was like an
This is too much.
amazing
Thanks.
presentation.
Thank you.
I was curious, you have so many interesting collaborations in different places in the world, and the people that you're working with would have I would imagine, a vested also interesting curiosity about advancing some of these techniques and material possibilities. And so I'm the other side of it, the client side of it. I was curious how you find people that can get equally invested in that as an outcome, because I know, I mean, it would relate to the economies of building for them, but also when you're talking about these an immense sort of housing deficiencies and wanting to scale it up. How do you find those partners, or how do you kind of cultivate those relationships? I'm curious.
The short answer is I don't know. I'm still trying to figure that out, because I think that is, you're absolutely right. I think that is the best way to accomplish it. I've rarely had success on the client side getting pressure for, so basically a precast manufacturer isn't going to try something new until a client insists on it, almost always, because it's dangerous for them to take on a new thing without someone paying for it. And so actually, weirdly enough, I started this recent collaboration with University of Virginia where they were building a new garage with a precaster that I had already started talking to about my research. And so UVA asked them, what are you doing to reduce the carbon of your concrete construction? And they said, we're researching with one of your professors. And the truth was they hadn't actually done anything yet. But because the client was interested, they saw that as an opportunity to try new things. And so they could push for that. And so UVA came back around and said, we just found out about your work from these people who are building a garage right next door to your school. And so that turned into a conversation where over the summer we've started researching the fact that almost no school has a goal in terms of embodied carbon. So UVA is trying to essentially document all their recent construction with realistic metrics of the embodied carbon, and then using that as a guide that they can start to put in their RFPs. And so if they call for companies to put a proposal for a parking garage, you now will have to do an LCA at some point. You'll have to have some kind of baseline metric that might be based off of UVA's data for the embodied carbon. All of this is possible because the client does want to be a leader in this, and they're trying to build institutional buildings that should last 100 years, not the 30 to 40 years that is often the case. So that's one, but that was just luck. That was literally like, I happened to be talking to this company and UVA hired them for something. So I do think like there's evidence of Google, for instance, pushing in their headquarters new technologies, and that allowed for manufacturers to try things that they'd already been wanting to try. That kind of thing, if you can get a big enough client to invest in a new solution, even if it won't be cost effective for them, to me is the best way. And universities are fantastic clients in that case. But I'm still trying to figure it out.
Yeah, but that's a great thing to build on, right?
Yeah,
That sort of intelligence of these
Exactly.
relationships and how you get them to add value,
Yeah.
to perceive the value.
Yeah. It's similar to LEED. Like how do we, LEED 5 is the first time where it just rolled out where embodied carbon even really becomes a point. And it's still not super in depth, but it's actually a step further than we've seen, where they're requiring LCAs, requiring them to use certain tools to get this set of points for LEED.
LCA is life cycle analysis for those of you who don't.
Yeah, which is a really hard science, and most people don't have the capacity. Companies will hire consultants, and every consultant does it a little differently, and every tool does it a little differently. So it's still kind of a mystery. What I always say, though, is that the accuracy is not as important as the reductions. And so if you're able to get any baseline, 50% off your baseline is still 50%. And so that's what we go for, which is why I use embodied energy and carbon sort of interchangeably, depending on the data I have available to me. It's a great question, though.
Can I also add, I think like one thing I noticed with the tools that you're deploying is that they're designer facing.
Right.
Right, and I think that's a really important thing is that, for designers, especially, people like eventually like us, what we need is like 80, 90% accuracy. We don't need it to be 100%, right?
Absolutely.
That'll come later down the line for the schematic design phase. That 80% with machine learning is like fast, right? Like you don't have to wait for the calculation.
Absolutely.
And I think that's a critical part, at least in the sort of design chain.
Yeah.
But I'm also curious, like off of this discussion about clients and risk, is that you're working kind of in opposite territories, both in like, okay, maybe a more capitalism driven, right, sort of, economic driven side, where on the other side, there's kind of actually a sort of humanitarian crisis side to it.
Yeah.
And then like how to kind of negotiate the two opposites is kind of really interesting. Also the risk, right? Like you're kind of talking about beta testing things, like companies like Google or Apple might be able to beta test certain things, right? Because they have the sort of portfolio to take on the risk. But then I think in the opposite sense, I think in concepts like India, there's not that much to lose anyway, so they can also try out things that maybe we wouldn't try.
Yeah, 100%. Just like you were talking about with LTU being very nimble with how they plan things and get students and force them to listen to me talk, is that like those countries are willing to try anything. They're desperate for solutions. They're nimble. Sometimes that's a dangerous thing because a lot of people take advantage of it. Like I remember going to northern India where people are experimenting with unreinforced, beautiful shaped vaulted structures. This is a terrible idea in many ways, partly because that requires a sort of level of, if you don't know, some of the stuff I showed by other people, really amazing structures that can be compression only. Northern India, most of it's earthquake, seismically active zone. And so it's a really dangerous thing to try in those areas. And so we had to be kind of careful who we work with, because sometimes that nimbleness means that they're willing to work with anybody who either has the name or the money to try it out. Sure. It's our responsibility to actually be honest about when our technology makes sense. So yeah, that's the one little caveat, but I completely agree.
Right. Oh, well, I'll take one last question back up there, and then I think we'll have to wrap up.
So you've presented kind of an interesting form here.
Yeah.
And I was wondering, do you think that this kind of form is applicable to more traditional architecture or culturally significant architecture in certain areas? Do you think that this could be integrated there while still preserving that culture?
Do you mean like the literal shape of the beams?
Literal shape of
Yeah, that's a great question. Oh, brings in some really interesting points where I love visiting historic stone structures, for instance, where we often talk about the ornament and the detailing actually being a way to resolve a structural problem. I think if we kind of go back far enough in a lot of construction technology, what we find is that certain forms are chosen because they didn't fall. Over and over again, we iterated and we found that they structurally didn't fail. It's the same with the Palladian proportions. Those were based off of, in some senses, they were based off of harmony and a human feeling for what's correct, but they were also based off of how far you could span with a stone. And so I think in one sort of more theoretical way, I see it as all kind of part of the same spectrum. Sometimes people will just look at the shape and say that doesn't look like what we're used to, and that's the interesting thing, is trying to say a parking garage with a curved fish belly beam is going to save 50% material. Even if it looks a little different, it's going to save material. But if I found someone who was really worried about how the beam looks, what is really important about the flexibility of our design methods or the tools that we're trying to develop is that we could still work with a company that doesn't want to do anything but extrude blocks that are exactly the same size and prove that you could still have something that essentially looks exactly the same but saves you 15-16% of the material. It's, depending on how open-minded you are, there's more opportunities to save, and I think it's more of an incremental thing. We don't go for the crazy beams that I love showing, especially to designers. Sometimes I have to work with just beams that look exactly the same but are more efficient. Does that make sense? It's a good question, and honestly, like a bigger one that we could spend a whole lot more time talking about. Thank you.
All right, please join me in thanking Mohamed
Thank you all
for
so
his
much.
time. And he'll be around if you want to talk to him.
Yeah, and my email's up there if you ever want to reach out. Totally fine. Nice to meet you all. Thanks.